Hello there, and welcome to The Wood Sleepy Scientist, where curiosity gets cozy and science takes the scenic route to slumber. Tonight's gentle journey is all about one of the most mysterious forces we live by but barely understand: time. It slips through our fingers, shapes our days, and occasionally plays tricks on us, especially when we're waiting for a kettle to boil. But before we unravel the ticking tapestry of time, I'd love to know, where in the world are you watching from? And what time is it for you right now? Fitting, isn't it? A video about time, and here we are, scattered across time zones, each of us arriving at this very moment in our own unique slice of the clock. If you find this voyage soothing, intriguing, or just a nice way to unwind after a long day, I'd be ever so grateful if you gave the video a like and maybe subscribed. It helps this little corner of calm reach others who might need a peaceful pause too. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll have learned something about the fabric of the universe before you drift off. So settle in, slow your thoughts, and let's begin. Because somewhere between seconds and centuries, dreams and daylight, lies the story of time. Time has a funny way of stretching and shrinking, doesn't it? 10 minutes spent stuck in traffic can feel like an eternity, while 10 minutes on your favorite hobby disappears faster than the last biscuit in the tin. And yet clocks tick forward at the same rate, second after second, minute after minute. So what's going on? The answer begins not with physics, but with your brain. Our perception of time, that internal sense of when things start and end, is surprisingly flexible. Psychologists call it subjective time, and it's heavily influenced by things like attention, emotion, and memory. In other words, how you feel about time can be very different from how time is actually passing. Let's start with the oddity of waiting. Imagine you're in a doctor's waiting room. The walls are beige, the magazines are ancient, and the clock ticks loudly in the corner like it's trying to win a competition for the world's most annoying sound. 5 minutes there can feel like half an hour. That's because your brain is starved for stimulation. When not much is happening, your attention turns inward, and that internal focus makes you more aware of each passing second. Compare that to a lively conversation with a friend or getting lost in a good book. In those moments, you're fully engaged, and your brain isn't keeping track of time so closely. It's like your mind goes, we're busy, no need to watch the clock. And before you know it, hours have flown by. This is sometimes called the flow state, a term coined by psychologist Mihaly Csikszentmihalyi, where your sense of time fades into the background as you become fully absorbed in the present. Interestingly, the novelty of an experience also plays a role. When you encounter something new or unfamiliar, your brain takes extra time to process and store the memory. Later, when you look back, it feels like more time must have passed because there's more mental footage of the event. That's why your childhood summers seem to stretch on forever. Your brain was constantly encountering new experiences, and it logged every bit of it. As we get older and routines set in, our brains get more efficient at compressing memories. Fewer highlights, shorter reels. Time seems to speed up. Emotion plays a part too. Studies show that fear and anxiety can slow our perception of time, while joy and excitement speed it up. There's even a theory that in dangerous or intense situations, your brain creates denser memories, giving the illusion that time has slowed down. This is sometimes reported by people who've been in car accidents or other emergencies. It's not that time actually slows down, it's that your brain records more details per second, creating a sort of slow-motion playback effect. Then there's the curious case of boredom. You've probably heard the phrase, "time flies when you're having fun," but the opposite, "time crawls when you're bored," is equally true.
Neuroscientists have found that when we're bored, the brain's internal pacemaker, or yes, that's a real term, becomes more active. This creates more pulses in our perception, making time seem to drag. It's like having an over-enthusiastic drummer in your head, tapping out every beat of a dull moment. Cultural background and language also influence how we perceive time. In English, we often talk about time as if it's a resource. We spend time, save time, or run out of it. Some languages, like Hopi or Yanomami, don't treat time as a line you move along, but more like a landscape or a set of conditions. This shapes how people in different cultures think about the future and the past. In fact, in some parts of the world, people point behind them to indicate the future because it's unknown, and in front of them to show the past because it's already visible. Quite the opposite of how we usually picture things. But what about our inner clocks? Surely there must be some kind of biological mechanism ticking away, giving us at least a rough idea of the passage of time. There is, sort of. Humans have something called a circadian rhythm, a 24-hour cycle that helps regulate sleep, body temperature, and hormone levels. But that's more like a daily timer than a stopwatch. For shorter periods, seconds, minutes, scientists believe we use a kind of mental timekeeper, often compared to a stopwatch in the brain. This system involves a network of brain regions, including the basal ganglia and the cerebellum, and it seems to rely on a steady stream of neural pulses. When we estimate how long something takes, we're subconsciously counting those pulses. That said, we're not always good at it. Our time estimations can be wildly off, especially when we're multitasking, distracted, or emotionally charged. There's even a psychological phenomenon called the return trip effect, where the journey back from somewhere feels shorter than the trip there, even if it takes the exact same amount of time. Why? On the way there, your brain is actively processing new information. On the way back, it already knows the route, so the experience feels faster. And let's not forget the most universal distortion of time known to mankind, the snooze button. Somehow, those 9 minutes between alarms feel shorter than any other 9 minutes in the universe. While there's no hard science behind that specific feeling yet, it's probably another case of disrupted sleep, incomplete consciousness, and our fuzzy internal stopwatch just throwing up its hands and giving up. So what is time? At least as we experience it, it's not just a number on a clock or the shadow of a sundial. It's a feeling, a perception, a trick of memory and attention. It changes with our mood, our age, and even the language we speak. It speeds up when we're in love, slows down when we're scared, and sometimes, just sometimes, seems to vanish altogether. And while physics may eventually explain what time is on the grandest scales, our personal sense of time will always be something deeply human, wobbly, wonderful, and at times delightfully unreliable. If time is mysterious, then our efforts to measure it are a testament to both human ingenuity and impatience. From ancient sundials to atomic clocks, we've spent millennia trying to wrangle this invisible force into something we can see, count, and ideally schedule around.
because while time may wait for no one, humans are very fond of asking it to hold on just a minute. Let's start in the deep past, when the first timekeepers weren't clocks or calendars, but the sky. Our ancestors were expert observers of the heavens, the rising and setting of the sun, the phases of the moon, the seasons shifting like slow tides. These were nature's earliest calendars, no batteries required. The ancient Egyptians were among the first to formalize timekeeping. Around 1500 BCE, they built towering obelisks that acted as giant sundials. By tracking the shadow's movement, they could divide daylight into segments, though the lengths of these segments changed with the seasons, an hour in summer, quite a bit longer than one in winter. It wasn't exact, but it was good enough for farming, prayers, and organizing society, which even then was likely running late for something. Water clocks came next. These devices, used by both the Egyptians and later the Greeks and Chinese, measured time by the steady flow of water from one vessel to another. They were simple, consistent, and could work at night, a big upgrade from sundials. Some were surprisingly elaborate, with gears and figures that chimed the hours or even rang bells. You could say they were the original smart devices, just wetter. Meanwhile, in Mesoamerica, the Maya developed intricate calendar systems that tracked lunar and solar cycles with astonishing accuracy. Their long count calendar could measure spans of time covering thousands of years. For a civilization that didn't have metal tools or beasts of burden, their grasp of time was nothing short of cosmic. But back in Europe, it wasn't until the Middle Ages that mechanical clocks began to tick their way into history. At first, these were large, unwieldy contraptions installed in church towers and monasteries. They didn't have faces or hands. They just rang bells at regular intervals to mark the passing hours, mostly to remind monks when to pray. You might say monks were the world's first alarm clock users, albeit far more serene about it than most of us at 6 a.m. One of the first major leaps forward came in the 14th century with the invention of the verge escapement, a clever bit of engineering that allowed for a more controlled and regular release of energy. This made it possible to build smaller, more reliable mechanical clocks. Eventually, clockmakers added dials and hands, so people could actually see the time, not just hear it toll. From there, the pace of innovation began to tick faster. By the 17th century, the pendulum clock entered the scene thanks to the brilliant Dutch scientist Christian Huygens. Pendulum clocks were accurate to within a minute a day, a staggering improvement over earlier designs that could drift by hours. If time was a horse, the pendulum was the saddle that let us ride it with more confidence. The need for even more precise timekeeping became critical during the age of exploration. Sailors desperately needed to know their longitude, and that required knowing the exact time at a fixed reference point, like Greenwich. Enter John Harrison, an English carpenter who spent decades inventing marine chronometers, ultra-precise clocks that could survive the rocking and rolling of a ship at sea. His fourth model, H4, changed navigation forever and earned him a belated but well-deserved place in history. Also, possibly a few eye rolls from people who had been using stars and gut instinct until then. By the 20th century, we entered the age of quartz. Quartz crystal oscillators, first developed in the 1920s, revolutionized timekeeping. When subjected to an electric current, quartz vibrates at an incredibly stable frequency. These vibrations were used to keep time with far greater precision than anything mechanical. Suddenly, clocks and watches could be cheap, portable, and accurate enough to keep the trains running on time, or at least give us no excuse when they didn't. But even quartz has its limits. If you want to know the most accurate time on Earth, you'll have to go atomic. Atomic clocks, first developed in the 1950s, measure time using the natural vibrations of atoms, usually cesium or rubidium. A cesium atom, for instance, oscillates exactly 9,192,631,770 times per second. That number isn't just trivia. It's the official definition of a second, according to the International System of Units. These clocks are so precise that if you ran one for 100 million years, it would be off by less than a second, which is great, assuming you have 100 million years to wait for your tea to steep. Today, atomic clocks are used to synchronize everything from GPS satellites to internet servers, telecommunications, and global financial systems. Without them, your phone's map wouldn't work, your bank transactions would be chaos, and half the world would miss their Zoom calls. Time, once measured by dripping water and sun shadows, now depends on atoms flipping like microscopic metronomes in high-tech vaults. And yet, despite all this precision, time still feels strangely personal. We can divide it into hours, minutes, and seconds. We can watch it scroll by on digital screens. But no matter how finely we slice it, we each live it differently. So why did we begin measuring it in the first place? Some say it was to regulate prayer. Others to grow crops, mark seasons, or schedule trade. But maybe, just maybe, it's because humans, for all our love of stories and stars, are deeply comforted by rhythm.
The steady beat of time, no matter how elusive, gives shape to our days. It offers order in chaos. A tick, a tock, a tiny whisper from the universe saying, "You're here now." And that, after all, is what time has always been. Not just a measurement, but a companion. For most of human history, time was a local affair. It rose with the sun, ended with the stars, and ambled through the hours at the mercy of bells, birdsong, or an enthusiastic rooster. But then came Isaac Newton, a man who didn't just want to describe the world, but to pin it down. And that included time. Newton, the 17th century English physicist with the famously dramatic hair and a knack for apple-related anecdotes, gave the world a model of the universe that would dominate science for over 2 centuries. In his view, space and time were like a grand invisible stage on which the drama of the universe unfolded. The actors, planets, apples, cannonballs, and eventually bicycles, moved about, but the stage itself never changed. Time in this picture was absolute. It ticked along at a constant rate, everywhere, for everyone, forever. This concept, absolute time, was central to Newton's physics.
In his own words, absolute, true, and mathematical time of itself and from its own nature flows equitably without regard to anything external. In other words, time is like a river that flows at a steady pace, regardless of whether anyone is watching, counting, or floating along in a canoe. It made intuitive sense. Drop an object today or tomorrow, here or another city, and Newton's equations could tell you exactly where it would be at any point in time, assuming you had enough coffee and a solid grasp of calculus. Time was the steady backdrop against which motion, force, and gravity did their thing. Newton's absolute time gave scientists a powerful tool. It allowed them to describe motion in precise terms, to synchronize events, to create reliable predictions. If you wanted to calculate the orbit of a planet, the swing of a pendulum, or the fall of a cannonball, you could now plug it all into one neat mathematical framework. Time in this model was universal, the same everywhere, for everything, ticking along in perfect impartial harmony. But for all its usefulness, this idea came with a rather large assumption that time was a thing in itself, existing independently of the stuff happening within it, a kind of invisible metronome, keeping the beat of the cosmos. There were, however, a few dissenting voices. The philosopher Gottfried Wilhelm Leibniz, Newton's intellectual rival and co-inventor of calculus, didn't buy into the idea of absolute time, or Newton's version of calculus for that matter. Leibniz argued that time was not some universal backdrop, but a measure of change, a way of describing the order of events. Without events, he claimed, there is no time. It's not a thing on its own, but a relationship between things. Imagine a clock in a completely empty universe, ticking away in total silence and darkness. For Newton, that clock is still measuring time. For Leibniz, it's just a fancy paperweight with no one to notice. To him, time only has meaning when things happen. Newton wasn't having it. He insisted that time was real and flowed regardless of what was going on, which, to be fair, does match the feeling of waiting for a pot to boil. Newton's ideas eventually became the foundation of what's now called classical mechanics, and for a very long time, classical mechanics worked beautifully. It could describe the motion of falling objects, swinging pendulums, the orbits of the moon and planets, and even with enough effort, the motion of a juggling unicyclist. So, it's worth pausing to admire just how successful Newton's framework was. For hundreds of years, scientists relied on his absolute time and space to explore the natural world. Clocks became more precise. Navigation improved. Engineering leapt forward. Steam trains ran on time, or at least had a better excuse when they didn't. But here's the twist. As good as Newton's model was, it eventually started to crack under pressure. In the 19th century, scientists studying light and electromagnetism noticed strange things. Experiments suggested that the speed of light was always the same, no matter how fast you were moving. That didn't make sense in Newton's universe. If a car speeds up, it should catch up to light a little more quickly, right? But it didn't. The light always sped away at the same pace. This problem simmered for a while, until a young patent clerk named Albert Einstein. But we'll leave his entrance for another chapter.
Suffice it to say, he would take Newton's absolute time, give it a polite nod, and then turn it completely upside down. Still, Newton's idea of time as an ever-flowing universal quantity left a deep imprint on science and culture. We still speak of time as something we can waste, spend, or save. All phrases that make sense if time is a commodity trickling away. Our workday, school bills, and microwave settings all run on the belief that time ticks the same for everyone. And in many everyday situations, that's still perfectly true. When you're baking a cake, catching a bus, or trying to remember when your online order is due, Newton's time works just fine. It's only when we start dealing with high speeds, strong gravity, or extremely small scales that Newton's picture begins to blur. So in the grand story of time, Newton gave us a solid middle chapter, a vision of a predictable, mechanical universe running like clockwork. He brought order to the cosmos and made time something we could measure, trust, and, if only briefly, understand. But time, as we'll see, has more than one personality, and while Newton's time is wonderfully logical, the universe may not be quite so straightforward. If Isaac Newton imagined time as an endless river flowing at a steady pace for everyone, Einstein came along and said, "Actually, it's more like a wibbly-wobbly trampoline." That's not a direct quote, but it's surprisingly close to the truth. In the early 20th century, Einstein upended our understanding of time with a set of ideas so radical they reshaped the very fabric of reality. He called it relativity, and it came in two parts: special relativity, and later, general relativity. Both of them had plenty to say about time, none of it particularly intuitive. Let's begin with special relativity, published in 1905 when Einstein was just 26 and working at the Swiss Patent Office, probably spending his lunch breaks rewriting the universe. One of the key ideas of special relativity is that the laws of physics, including the speed of light, are the same for all observers no matter how fast they're moving. Now, this causes a problem for Newton's absolute time. In Newton's world, if two people are moving at different speeds, they still agree on when things happen. But in Einstein's world, that's not necessarily true. Events that appear simultaneous to one person might not look simultaneous to someone moving at a different speed. This leads to one of the strangest consequences of special relativity: time dilation. Simply put, the faster you move, the slower time passes for you relative to someone standing still. If you were to board a spaceship and zoom off at near light speed, your onboard clock would tick slower than the one back on Earth. You'd age more slowly. Your hair would take longer to grow. You'd miss entire seasons of your favorite shows. This isn't just science fiction. It's been observed. One famous experiment involved flying atomic clocks around the world on airplanes. When compared to identical clocks that stayed on the ground, the airborne ones had ticked ever so slightly more slowly. Not enough to notice, unless you're very punctual, but enough to prove that time really does slow down with speed. And then there's the famous twin paradox. Imagine two identical twins. One boards a spaceship and flies around the galaxy at high speed. The other stays home, feeds the cat, and waits. When the traveling twin returns, they'll be younger than their sibling. Not because they used a great skincare routine in space, but because their time actually passed more slowly. The paradox isn't a contradiction. It's a feature of relativity. A confusing, mind-bending feature, but a real one. But speed isn't the only thing that messes with time. In 1915, Einstein expanded his theory into something even bigger: general relativity. This theory dealt with gravity and revealed that gravity, too, can warp time. General relativity describes gravity not as a force, but as the curvature of space-time caused by mass. The more massive an object, the more it bends space around it, like placing a bowling ball on a soft mattress.
If time were painted onto that mattress, it would stretch and warp along with the space. What this means is that time runs more slowly in the stronger gravitational fields. If you stand next to something really massive, like a black hole or your friend's overpacked suitcase, time ticks more slowly for you than someone farther away from the mass. Again, this isn't just theory. It's been measured on Earth. In one experiment, two super-precise atomic clocks were placed at different altitudes, one at the base of a mountain and one at the top. The clock lower down, closer to Earth's center of gravity, ticked a tiny bit more slowly. Even a height difference of just a few centimeters can cause a measurable change in time. So yes, technically, your head is aging faster than your feet. This phenomenon, called gravitational time dilation, has real-world consequences. GPS satellites orbiting Earth experience both types of time warping. They are moving fast, which slows their time, but they're also farther from Earth's gravity, which speeds their time up. To keep your phone's map accurate, their onboard clocks are constantly adjusted to account for these distortions. Without those corrections, your location would be off by several kilometers within minutes. Time doesn't just pass, it wobbles, and technology has to wobble with it. So, what does all this mean for our understanding of time? Einstein showed us that time isn't an absolute, universal river. It's more like a stretchy fabric woven together with space itself. It can expand, contract, bend, and twist depending on speed and gravity. And that means your time, the pace at which you experience the universe, depends on where you are and how you move. It's a deeply strange idea, but also kind of beautiful. Time is no longer the same for everyone, everywhere. It's personal, relational, a bit like your taste in tea. Einstein's work didn't just rewrite physics textbooks. It changed how we see reality itself. Time is not a fixed background. It's part of the dance, shifting with the rhythm of matter and motion. And even though most of us don't feel time stretching or shrinking in our daily lives, every second we live is shaped by these subtle distortions. So next time someone tells you they're running out of time, you can gently remind them, actually, time is running out differently depending on your velocity and proximity to gravitational mass. Then pause, smile, and maybe duck. Let's imagine, just for a moment, that you wake up one morning and find everything running backwards. Toast leaps out of your mouth and lands perfectly buttered on a plate. Your tea grows hotter as you drink it. Raindrops fly upward into the sky. Strange, certainly. Impossible? According to the laws of physics, not exactly. This odd little thought experiment leads us to one of the most intriguing questions in science. Why does time seem to have a direction? In most of the fundamental laws of physics, from Newton's laws of motion to the equations of quantum mechanics, time doesn't really have a preferred direction. They work just as well backwards as they do forwards. If you were to film two particles colliding and play it in reverse, the physics would still check out. No alarms would go off in the equations. And yet, in everyday life, time feels like a one-way street. Eggs break but don't unbreak. Paper burns but ashes don't reassemble into books. We remember the past but not the future. So why this disconnect? Why does time at our human scale march relentlessly from yesterday to tomorrow? Enter the concept of the arrow of time. The arrow of time is a metaphor used to describe the one-way direction in which time appears to flow from the past to the future. And the key to understanding this arrow lies in one of the most important and occasionally untidy laws of physics, the second law of thermodynamics. This law tells us that in a closed system, like the universe, entropy always increases over time. Entropy is a measure of disorder or randomness. In other words, things tend to go from tidy to messy. You can scramble an egg, but you can't unscramble it. Your desk will naturally become cluttered unless you actively organize it. Socks will always disappear mysteriously, but never reappear in pairs. This tendency toward increasing entropy gives time its arrow. It's why we experience events in a particular sequence. The low-entropy past becomes the high-entropy future, and there's no reversing the flow. Unless you're a time traveler or a fictional wizard with a very specific spell. Think of it this way. Imagine a glass shattering on the floor. That's a high-entropy state. The shards are spread out and energy has been lost in the chaos. It's extremely unlikely that all those fragments will spontaneously leap back together into a perfect glass.
Not impossible, just astronomically improbable. And that's the key. The laws of physics allow for time reversal in theory, but probability stands firmly in the way. This leads to one of the most intriguing and slightly unsettling questions in cosmology. Why was the universe in such a low entropy state to begin with? After all, if entropy must increase, there had to be a starting point, a kind of cosmic neat and tidy drawer from which all this disorder could unfold. The leading theory is that the early universe, just after the Big Bang, was incredibly uniform, smooth, ordered, low entropy. Over billions of years, gravity and expansion did their thing, and the universe got clumpier and more chaotic. Galaxies formed, stars exploded, and socks disappeared at an accelerating rate. But why it started that way is still one of physics's biggest open mysteries. Some scientists suspect the answer lies in the deep relationship between entropy, time, and the geometry of space itself. Others wonder if the question is even meaningful or if we're just asking it from the wrong angle, like a goldfish trying to understand water. There are other arrows of time too, each pointing the same way. There's the psychological arrow. We remember the past, not the future. That's because memories require physical processes in the brain that leave behind traces, and those traces are part of entropy increasing. You can't remember the future because it hasn't happened yet, and no traces have been laid down. There's the causal arrow. Causes precede effects. You flip a switch and the light comes on. You don't turn on a light and then decide to flip the switch. Again, this follows entropy. Flipping the switch adds energy. Light spreads out, and the universe becomes a slightly messier place. And finally, there's the cosmological arrow, the expansion of the universe itself. The fact that galaxies are moving away from each other, space is stretching, and everything is cooling down over time gives a sense of direction to the cosmos. If the universe were contracting, would time feel like it were running backward? That's a theoretical playground scientists still enjoy exploring. It's worth noting, though, that these arrows, entropy, memory, causality, and cosmic expansion, all line up. They all point in the same direction, which is comforting in a way. It suggests that time isn't just a random illusion, but something deeply woven into the structure of reality, a direction carved by the flow of energy, the march of disorder, and the gentle spreading out of everything from a once very tidy beginning.
But not everyone is convinced that time as we experience it is fundamental. Some physicists argue that the arrow of time is an emergent phenomenon, something that arises only when complex systems like us observe simpler ones like tea cooling or egg scrambling. In some interpretations of quantum mechanics, time is just another parameter, not a force, not a flow, just a label for different states. The universe doesn't feel time. We do. And that's the curious thing. No matter how deeply we dig into entropy, probability, or equations, time continues to be both incredibly real and maddeningly elusive. It's something we ride like a current, but we can never quite step outside of it. We don't know what's ahead, we can't go back, and yet we live our lives by its rhythm, comforted by the fact that the future, however uncertain, is always on its way. So the next time you feel like time is slipping away, remember it's not lost. It's just following the one rule it's really good at: moving forward, increasing entropy, and leaving a trail of mismatched socks and empty teacups. If classical physics treats time as a dependable train schedule, always on track, ticking along steadily, then quantum mechanics treats it more like a jazz improvisation, flexible, mysterious, sometimes dissonant, and just when you think you understand what's going on, it throws you a cat in a box and asks you to consider whether it's both alive and dead. Welcome to the quantum world, where reality gets fuzzy and time becomes more of a polite suggestion than a fixed rule. In the classical universe, you can point to an object and say, it's right there doing that at this exact moment. But in the quantum realm, particles don't have neat possessions or momentum. Instead, they exist as probability waves, mathematical clouds of where they might be and what they might be doing.
So, where does time fit into all this? Surprisingly, time doesn't play the starring role in quantum mechanics that it does in classical physics or general relativity. In fact, it mostly shows up as a background parameter, something we plug into the equations to keep things moving, like pressing play on a simulation. Take the Schrödinger equation, the foundation of non-relativistic quantum mechanics. It describes how a quantum system's wave function, that weird cloud of probabilities, evolves over time. But unlike in relativity, time in this equation isn't something that bends or stretches. It's just there, a silent spectator, an external stopwatch that never changes, never warps, and certainly doesn't ask for attention. This creates a curious split. On one hand, quantum mechanics describes the evolution of states over time, but it doesn't explain what time is. It treats time as a fixed, absolute backdrop, much like Newton did, while space and matter are all jiggling unpredictably in front of it. But things get even stranger when you introduce quantum gravity, the theoretical attempt to merge quantum mechanics with general relativity. These two theories are the Diran twin titans of modern physics, but they don't get along well at parties. In general relativity, space-time is dynamic. It can stretch, curve, and evolve depending on the matter and energy within it. Time is not absolute. It's part of the fabric of the universe. But in quantum mechanics, time is fixed and unbending, a kind of cosmic metronome in the background. Trying to unify these two views is like trying to choreograph a ballet using instructions from a heavy metal concert. This leads us to what physicists call the problem of time in quantum gravity. When you try to describe the whole universe quantum mechanically, space, matter, everything, you find something odd. Time disappears.
One of the equations that pops up in quantum gravity is the Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe. It looks a lot like the Schrödinger equation, but without any time variable. It's timeless. There's no past, no future, just an eternal present, a giant now. So what's going on? Is time real, or is it just an illusion created by the way we experience change? Some physicists believe that time is emergent, not a fundamental part of reality, but something that appears when you zoom out far enough, like temperature. An individual molecule doesn't have a temperature, but when you group trillions of them together, temperature emerges as a useful description. In the same way, time might emerge from the complex interactions of many quantum systems. Others look to entanglement, the bizarre quantum phenomenon where two particles become linked and can influence each other instantly, even across vast distances. Some theories suggest that the arrow of time, and maybe even time itself, could arise from the growth of quantum entanglement. The more tangled the universe becomes, the more time seems to flow. And then there's the many worlds interpretation. In this view, every quantum event and every coin flip, every measurement, causes the universe to branch into multiple parallel realities. There's no randomness, just an infinite splitting of timelines. Time, in this view, isn't a river. It's a vast, ever-branching tree. Every decision you make creates a new twig. Somewhere out there, there's a version of you who didn't forget their umbrella this morning. But if time is such a shaky concept at the quantum level, why does it feel so solid to us? Well, we live in a world where countless quantum interactions average out into a smooth, reliable reality. Our brains, made of trillions of particles and neural circuits, are hardwired to perceive cause and effect. We wake up, brush our teeth, eat breakfast, and head to work, hopefully in that order. Time for us is a story, a sequence of events that gives meaning to change. And storytelling, as it turns out, is something humans are especially good at. We string events together into memories. We imagine futures. We define identities through time, past, present, and hopes for what's next. Whether or not time is fundamental, we certainly treat it as real. Still, quantum mechanics reminds us that underneath that comforting narrative lies something far more elusive. Time may not be the ticking of a clock or the turning of a page, but the unfolding of possibilities, the evolution of probability, the hum of reality, tuning itself ever so slightly with every passing moment. So, while your wristwatch says it's 10 minutes to midnight, quantum physics whispers, well, yes, from a certain point of view. Time isn't just something tracked by ticking clocks or orbiting planets. It's also humming quietly inside you, in your cells, your sleep, your appetite, and even your mood. Whether you're a night owl, an early bird, or a perpetually groggy pigeon, your body is running on its own internal clock, and it's a very old one. This internal clock, or more precisely, a network of them, is what scientists call the circadian rhythm, from the Latin circa diem, meaning about a day. Circadian rhythms are the biological processes that follow a roughly 24-hour cycle. They regulate everything from when you feel sleepy to how your body processes food, and they're found in nearly all living things: humans, plants, animals, fungi, even some bacteria. If it's alive and vaguely organized, it probably tells time. The master conductor of your circadian orchestra is a tiny region in your brain called the suprachiasmatic nucleus, or SCN for short. It's located in the hypothalamus, just above the point where the optic nerves cross. A very strategic position because it allows your body clock to sync up with light. When your eyes detect sunlight in the morning, the SCN gets the memo and sends out signals to adjust everything from hormone levels to body temperature. It's like your brain's version of tapping the snooze button on the sun. One of the SCN's most important jobs is controlling the release of melatonin, often called the sleep hormone. Melatonin levels rise in the evening, helping you feel drowsy, and fall in the morning to help you wake up. It's your body's way of saying, hey, maybe don't watch another episode right now. Whether or not you listen is another matter entirely. But here's the thing. While your circadian rhythm runs on a roughly 24-hour cycle, it's not exactly 24 hours. Most humans naturally run a little long, about 24.2 hours, give or take, which means that left entirely to our own devices, like in a cave with no clocks, we'd gradually drift out of sync with the actual day. Light exposure is what keeps us anchored. Morning sunlight resets the clock daily, keeping us in harmony with the Earth's rotation, or at least vaguely within range of our morning alarms. Disrupt this delicate system, and things get weird. Enter jet lag, humanity's least favorite travel souvenir. Jet lag happens when your internal clock is out of sync with your external environment, say when you fly across several time zones in a few hours. Suddenly, your brain thinks it's midnight when it's actually lunchtime, and your stomach, liver, and even your immune system are all deeply confused. That's because different parts of your body adjust to new time zones at different speeds. Your brain might reset quickly, but your digestive system might still be living in last week's time zone, wondering why dinner smells like airport pretzels. Another modern culprit is artificial light. Before electric lighting, humans were largely guided by natural daylight. We woke up with the sun and got sleepy when it set, a rhythm still preserved in traditional societies with little exposure to artificial light. But today, we're surrounded by screens and bulbs that emit blue light, which tricks our brains into thinking it's still daytime. This can suppress melatonin production and shift our circadian rhythm later, making it harder to fall asleep and more difficult to wake up. It's not so much that we're night owls now. It's more like we've invited a neon owl into our living rooms and handed it the remote. Interestingly, not everyone's circadian rhythm is the same. Some people are naturally morning types, or larks, who spring out of bed with suspicious amounts of energy. Others are evening types, or owls, who hit their creative stride just as everyone else is brushing their teeth. These chronotypes are partly genetic. So, if you're not a morning person, it's probably not just laziness. Your brain genuinely believes it shouldn't be awake yet. And honestly, who are we to argue with 1 billion years of evolution? Circadian rhythms also influence body temperature, which typically drops in the early morning and rises throughout the day, peaking in the late afternoon.
This is why many athletes and performers tend to do better later in the day. Their bodies are warmer, more alert, and running at peak efficiency. On the flip side, this is also why early morning presentations can feel like trying to do calculus while half frozen. But the influence of biological time goes beyond sleepiness and thermodynamics. It affects your metabolism, your immune system, your mood, and even how you respond to medications.
There's a growing field called chronopharmacology, the study of how drug effectiveness changes depending on the time of day. It turns out that timing matters. The same medicine might work better in the morning or evening, depending on what it targets and your body's readiness to absorb it. Plants, too, follow circadian rhythms. They open their leaves to sunlight during the day and close them at night. They even anticipate dawn, starting to stir slightly before the first rays hit. This isn't just a passive response to light. It's an active, internal cycle that persists even in constant darkness. The sunflower doesn't follow the sun because it sees it. It turns because it remembers. And in animals, from birds to bees to rodents, circadian rhythms help regulate everything from migration to foraging to hibernation. Even fungi, those mysterious forest floor dwellers, have internal clocks that govern spore release and growth cycles. All of this paints a picture of life on Earth as deeply intertwined with time, not the abstract kind measured by atomic clocks, but a biological time grounded in light and dark, warmth and cold, hunger and rest. A time that pulses through living things like a gentle drumbeat. So the next time you feel tired at 3 p.m. or unusually perky at night, it's not random, it's rhythm. Your body is dancing to an ancient, invisible beat, one that kept our ancestors safe and well-rested long before time zones, digital watches, or double-shot espressos. And while we may try to bend time to our will with alarms and schedules, deep down, our cells are still following the sun, slowly, quietly, faithfully. Have you ever noticed how time seems to play favorites? A holiday week flies by like a feather in the breeze, but the last 10 minutes of a Zoom call you didn't want to be on in the first place, that feels like you're trapped in a slow-cooking rice pudding of eternity. This isn't just poetic exaggeration. There is psychological time at work. That is the wonderfully warped way our minds perceive time's passage, which often has very little to do with clocks and calendars. If physics tries to describe time as it is, psychology tries to explain how it feels, and those two can be wildly different things. Let's start with perhaps the most basic distortion. Time flies when you're having fun. This cliché actually holds up to scientific scrutiny. When we're deeply engaged, laughing with friends, immersed in a hobby, or watching something genuinely riveting, perhaps even a sleepy scientist, we're not paying close attention to time itself. Our focus is absorbed in the moment, and our brain effectively stops counting the seconds. The result? Time appears to vanish. On the flip side, boredom stretches time like taffy when nothing is engaging us. Say you're waiting at the DMV, watching paint dry, or listening to someone explain crypto for the 15th time. Your brain starts clock watching, and time, like a watched pot, refuses to boil. You become hyper-aware of each passing second, and every moment feels longer than it actually is. There's also the peculiar phenomenon of retrospective versus prospective time. When you're in the moment, time might feel fast or slow depending on your engagement level, but when you look back on it, the effect can reverse. Let's say you spent a week hiking through unfamiliar terrain. During the week, the days might have flown by. But looking back, the trip feels long, packed with vivid memories. That's because novel experiences create more mental bookmarks. Your brain stores more detail, and that gives the impression that more time has passed. Contrast that with a week where you did the same routine every day. Wake, work, Netflix, sleep. It might have felt slow while you lived it, but in hindsight, it blurs together. Fewer bookmarks, fewer memorable moments, less perceived time. This is part of why time seems to speed up as we get older. When you're young, everything is new.
Your brain is constantly learning, recording, and marking the moments. Your first bike ride, first heartbreak, first awkward haircut, all logged in crisp detail. As we age, we settle into routines. Fewer surprises, fewer memory markers. Days blend into each other, and suddenly decades seem to have passed in a blink. It's not that time is going faster, it's that our brains are logging it less actively. We're building mental highways instead of wandering new trails. There's also the curious effect of emotional intensity on time. When we're scared or anxious, time often feels like it slows down. This isn't just dramatic storytelling. It's been tested in labs. People who experience sudden shocks like bungee jumps or simulated free falls report a feeling of stretched-out moments. One theory is that the brain under stress goes into overdrive, capturing more detail. Later, when we recall it, the dense memory gives the illusion of slow motion. But interestingly, time doesn't actually slow down in the moment. In experiments, people don't perform better during the event itself, they just remember it as longer afterwards. So, while your memory says, "That was the longest roller coaster drop of my life," your stopwatch says, "Actually, it was 3.2 seconds. Still impressive, just not Matrix level." Then there's attention, perhaps the most potent shaper of psychological time. When we pay close attention to time, like waiting for cookies to bake, we experience every tick of the clock. But when our attention is elsewhere, absorbed in music, reading, or conversation, time recedes into the background. This ties closely to mindfulness and meditation practices, which deliberately shift attention away from time. When we focus on the present moment, a breath, a sound, a sensation, time seems to dissolve. It's not that we enter a trance or lose touch with reality, it's that we stop measuring time and simply exist within it. For many, this feels profoundly freeing. You're no longer chasing the next hour, you're living fully in this one. On the more complex end of the spectrum, there are altered states of consciousness, states brought on by deep meditation, intense emotion, or certain substances where people report time slowing down, speeding up, looping, or disappearing entirely. Some even describe timelessness, not a distortion of time, but the absence of it, as if for a brief moment they stepped outside the river and looked at it from the bank. Neurologically, these experiences may involve changes in activity in the default mode network of the brain, a set of interconnected regions involved in self-referential thought, memory, and time processing. When this network quiets down, our normal sense of identity and time can dissolve, which might explain why your most timeless moments, or flow, stillness, often feel the most meaningful. Children, too, have their own unique relationship with time. For very young kids, time is fluid, imprecise, and mostly irrelevant. Ask a 5-year-old how long 5 minutes is, and you'll likely get an answer that involves forever or
until I finish this snack. Only as they grow and are introduced to clocks, schedules, and the dreaded phrase, just a few more minutes, do they begin to align with adult time. Some might argue that's the true loss of innocence. And finally, there's anticipation, our brain's built-in time machine. Looking forward to something makes time slow down. Is it Friday yet? While dreading something can do the same. We imagine future events in detail, rehearse conversations, worry over outcomes, all using the same neural machinery we use to recall the past. Time in this sense becomes elastic, stretched by hope and fear alike. So, is psychological time reliable? Not really. Is it logical? Often no. But is it deeply human? Absolutely. We may live in a universe of ticking atoms and rotating planets, but the time we actually experience, the time that colors our lives, is woven from memories, emotions, attention, and imagination. It's time felt, not measured. And maybe that's why it feels so personal, so strange, so beautifully inconsistent. Let's be honest, no discussion of time is truly complete until we ask the question that's launched 1,000 sci-fi novels, inspired countless thought experiments, and derailed more than a few dinner party conversations. Can we travel through time? Well, maybe, but it's complicated. Time travel, at least in theory, isn't entirely forbidden by physics. In fact, according to Albert Einstein's general relativity, the fabric of space-time is flexible. It can stretch, warp, and under the right incredibly extreme and possibly impractical circumstances, even loop back on itself. If that's true, then the idea of zipping to the past or future isn't completely out of the question. Let's start with the easy kind, traveling into the future. This one's not just possible, it's already been done. Remember time dilation from special relativity? If you move very fast, close to the speed of light, time slows down for you relative to someone standing still. If you zoomed around the galaxy in a spaceship at near light speed and returned to Earth, decades could have passed here while you'd only aged a few years. Congratulations, you've time-raved into the future. No flux capacitor required. This phenomenon has even been tested. Astronauts who spend months aboard the International Space Station experience a tiny bit of time dilation. They age ever so slightly less than their Earthbound counterparts. Not enough to notice without atomic clocks, but enough to prove the principle. They return to Earth microseconds in the future. Technically still on time for lunch, though. So, future time travel? Check. Done. Easy. But what about the real mind-bender, traveling into the past? Here, things get trickier. General relativity does allow for certain solutions to its equations that could, in theory, permit backward time travel. These include phenomena like closed time-like curves, loops in spacetime where an object could return to an earlier point in its own history. Think of it like walking a lap around the universe and ending up back at yesterday. One proposal involves something called a wormhole, a hypothetical tunnel connecting two distant points in spacetime. If one end of the wormhole were accelerated to near light speed and then returned to its original location, time at that end would lag behind. Step through the wormhole and boom, you've arrived in the past, at least in theory. The practical problems with wormholes are, well, monumental. First, we're not even sure they exist. Second, if they do, they may collapse instantly. And third, keeping one open would require negative energy, something exotic and not currently available in your average home improvement store. So while wormholes are fascinating on paper, building one might be slightly beyond our current engineering abilities, give or take a few centuries. But even if we could travel back in time, we'd immediately run into some rather sticky paradoxes. The most famous is the grandfather paradox. You go back in time, accidentally or perhaps carelessly prevent your grandfather from meeting your grandmother, and thus prevent your own birth. But if you were never born, how did you go back in time to begin with? It's a loop that logic can't quite untangle, a cosmic contradiction. There are a few ways scientists and philosophers have tried to make sense of this. One idea is the block universe model, where all moments in time, past, present, and future, exist simultaneously, like frames in a film reel. In this view, the timeline is fixed and unchangeable. If you go back in time, everything you do was always part of the past, so you can't change anything. You're just playing your role in an already written scene. Another possibility is the many worlds interpretation, borrowed from quantum mechanics. In this scenario, if you go back in time and change something, you don't alter your original timeline, you create a new branching universe where events unfold differently. You can stop your grandfather from meeting your grandmother, but it only affects that branch of reality. Your original self is still safely anchored in their own universe, free from paradoxes and awkward family dinners. There's also the cheeky and very scientific-sounding Novikov's self-consistency principle, which essentially says you can't create a paradox no matter how hard you try. If you go back in time, the universe will somehow prevent you from doing anything that would change the future. Try to assassinate your grandfather, and your gun will jam, or you'll trip, or he'll unexpectedly join a monastery. It's like the cosmos has a built-in insurance policy against timeline tampering. Still, all of this remains theoretical and highly speculative. No one has ever built a time machine. No one has ever documented a time traveler. Not for lack of trying.
And the internet is full of interviews with suspiciously modern-looking figures in old photographs. And physicists still debate whether the math permits or prohibits time loops. One interesting point: if backward time travel were possible, and if someone in the future eventually invents it, where are all the time tourists? Shouldn't we be knee-deep in visitors from the year 4000, taking selfies with dinosaurs or trying to blend in at medieval banquets? Some suggest time travel might be limited to the point of its invention. You can't go back to before the first time machine was created. Others think travelers might be incredibly discreet. Or, perhaps more realistically, time travel into the past is simply impossible, despite what the equations tease us with. And maybe that's for the best. As much as we fantasize about revisiting the past and fixing mistakes, reliving moments, buying absurd amounts of Bitcoin, perhaps time's one-way nature is part of what makes it meaningful. We can't edit our lives like a video. We move forward moment by moment, with all the richness, imperfection, and unpredictability that comes with it. Still, it's fun to dream. And who knows, maybe someone from the future is reading this right now, nodding quietly and thinking, "Ah, yes, the primitive beginnings of temporal theory." If so, welcome, and please don't spoil how this chapter ends. After traveling through the physics of clocks and the psychology of minutes, after bending time near black holes and wondering about wormholes, we arrive at perhaps the strangest question of all: does time actually exist? Now, that might sound like a philosopher's trick, the kind of thing you'd hear at 2 a.m. in a dorm room filled with empty tea mugs and earnest eyebrows. But it's a question that physicists, too, take seriously. Because when you peel back the layers of how we experience time and how we describe it mathematically, something strange starts to happen.
it starts to disappear. Let's begin with a reminder of how we usually think of time. For most of us, it feels like a river, flowing smoothly, carrying us from past to present to future. We're all floating downstream, unable to paddle backwards, only forward. Sometimes gently, sometimes in a rush, but always forward. This is called presentism, the philosophical idea that only the present moment is real. The past is gone, the future doesn't exist yet, and now is all there ever truly is. It aligns with how we live our lives, moment by moment, breath by breath, taking along with our clocks and calendars. But there's another idea, one that Einstein's theories of relativity helped make famous. It's called eternalism. And in this view, time doesn't flow at all. All moments in time, past, present, and future, already exist. The universe is like a four-dimensional block, sometimes called the block universe. Time isn't something we move through. It's a dimension we're part of, just like space. In this view, your childhood, your future retirement, and everything in between are all laid out like pages in the book. You don't become older. You already are older on some page, younger on another. You're not surfing time. You're a static thread woven into the fabric of a space-time quilt. Comforting? Maybe a little spooky? Also, yes. This concept arises naturally from relativity. Remember simultaneity, the idea that two things happen at the same time? Depends on your motion. Two observers moving at different speeds can disagree about what now means. That suggests there's no universal present moment, no cosmic stopwatch ticking for everyone, which makes the whole idea of a moving present a bit wobbly. If that's not enough existential spice, quantum gravity adds another twist. We touched on this in the quantum mechanics chapter. When you try to combine quantum physics with general relativity, time often drops out of the equations altogether. In the Wheeler-DeWitt equation, for example, there's no time variable. None. The universe, according to this view, is fundamentally timeless. But if time doesn't exist at the deepest level, why does it feel so real? One possible answer: emergence. Time, like temperature or sound, may not be a fundamental ingredient of the universe. Instead, it might arise from more basic relationships between things, patterns, changes, interactions. The way clouds form from molecules, or waves appear in water. Time, in this view, is something our brains extract from the way things change.
This is similar to how we perceive motion in film. A movie is just a sequence of still frames, but when shown rapidly, our minds perceive motions, a flowing narrative. Some physicists suggest that time might work the same way. What we perceive as the passage of time is really the brain stitching together changes in a fundamentally timeless reality. Enter physicist Julian Barber, who goes even further. In his view, time doesn't exist at all, not even as a parameter. Instead, the universe is a vast landscape of nows, complete timeless snapshots of the universe. These nows don't change or evolve. They just exist. Our experience of time, he argues, comes from the way these nows are structured and how memories embedded within them. A kind of cosmic photo album, if you like, with our consciousness flipping through the pages. It's a radical idea, but it raises an interesting possibility. Maybe the sensation of time passing is a feature of perception, not physics. After all, we humans are narrative creatures. We remember the past. We anticipate the future. We tell stories. We measure time because it helps us organize our experiences, plan our days, and understand change. Time is useful, perhaps essential, for sentient beings navigating a changing world. But that doesn't mean it's real in the way a rock is real, or a star, or a slice of cake, which also mysteriously disappears with the passage of time. Still, not everyone agrees that time is an illusion. Many physicists argue that even if time emerges from more fundamental processes, it still has real effects. Clocks tick, planets orbit, radiation decays. If we build a machine that consistently measures change, and that machine agrees with all the other machines, doesn't that make time real enough? Maybe that's the best answer. Time is real in the same way stories are real. Not because you can hold it or isolate it in a test tube, but because it structures the way things happen. It's the script that allows events to make sense, even if the script itself is printed on quantum paper that's written in a language we don't yet fully understand. So, does time exist? Well, perhaps not in the way we think it does. It might not be a flowing thing or a ticking clock behind the scenes, but it exists in our experience, our biology, our culture, and our equations. It exists in how we live and how we remember. It exists in every heartbeat and every bedtime story. And maybe that's enough, because whether time is fundamental or emergent, real or imagined, it gives shape to our lives. It reminds us that everything changes, that moments are precious, and that somewhere in the fabric of the universe, you are quite timeless here. And so, dear listener, we arrive at the end of our little voyage, or perhaps just another moment in the vast looping sea of them. We've wandered through ancient sundials and atomic clocks, ridden Einstein's warping waves of space-time, puzzled over paradoxes, and stared down the question of whether time exists at all. Along the way, we've seen that time is not just one thing, but many things. A rhythm felt in the body, a trick played by memory, a wrinkle in gravity, a story told by change. And now here you are, a little farther along your own timeline than when we began. But was it seconds, minutes, an hour? Or did the flow of words stretch and shrink like it so often does when the mind begins to soften into sleep? So let me ask you once more, gently, as I did at the start. Where are you listening from tonight? And what time is it right now in your little corner of the world? Funny, isn't it? After all this talk about time being relative, flexible, maybe even imaginary, we still anchor ourselves to it. A glowing number on a screen, the hush of late evening, the feeling of winding down breath by breath. And if you found any calm in this quiet expedition, if the wonders of the cosmos gave you peace, or the questions helped you drift gently into your dreams, I'd be ever so grateful if you'd like the video. Maybe subscribe and share this sleepy space with someone else who might need it. Time may be slippery, strange, and possibly a complete illusion,
But right now, here in this moment, it's just you, this voice, and the slow rhythm of rest. Sleep well, fellow traveler, wherever and whenever you are.